In this video, I will introduce the chain rule for finding derivatives. We will then consider some applications involving related rates, the behavior of the Gaussian curve, and a problem involving the time for a cube of ice to melt. Now, let's begin with the chain rule itself. Let y equal f of u be a function of the variable u, while u itself is a function of another variable x, say u equals g of x. Using Leibniz notation, the chain rule simply says dy dx equals dy du times du dx. You can think of that differential du in the numerator canceling with du in the denominator, as though these were ordinary fractions. There's an equivalent statement using function notation that we can use to write the chain rule. And here it is. The derivative of the composite of f and gx is equals to the derivative of f gx times the derivative of gx. These two statements, they look quite different, but in fact carry exactly the same information. I'll come back to the function notation that involves the dash a little later. For now, let's focus on the version of the chain rule using Leibniz notation and work through some examples. Let's consider this one. Y equals negative 3x plus 6 all squared. And we want to find the derivative dy dx. We can solve this, of course, by expanding the bracket to get the quadratic that we see here, and differentiating to get 18x minus 36. And we can factorize that too. We can also solve this indirectly using the chain rule. And we can put u equal to minus 3x plus 6. Therefore, y would be u squared. Now, according to the chain rule, dy dx is going to be equal to dy du, which we can see is 2u, times du dx, which we can see is going to be minus 3. So this product becomes 2u times minus 3, which is minus 6u. Converting back into an expression involving x, this becomes minus 6 times minus 3x plus 6, which quickly simplifies to 18 times x minus 2, which is the same answer we got earlier. In this example, there's about the same amount of work regardless of the method used. In more elaborate examples, the chain rule can save a lot of time and work. With little practice, you will be able to develop fluency quickly, and you will find the chain rule effective, powerful, and easy to use. Let's consider this next example. We want to find the derivative of y equal e to the minus x. Let's put u equal minus x. So y is equals to e to the u, and well, we know the chain rule. dy du is going to be e to the u, and du dx is going to be minus 1. So we end up with minus e to the u, which is minus e to the minus x. More generally, we can consider y equals e to the kx, where k is a constant, and imitate the previous calculation when k was equal to -1. Put u equal to kx so that y equals e to the u. Again, stating the chain rule. We have dy du is going to be e to the u, and the derivative of u equal kx is going to be k. So we can now write that the derivative of y equal e to the kx is k e to the kx. Now, you may be curious to know why the chain rule works. Let's look at the proof. Let's take the idea of canceling differentials in the numerator and denominator and relate this to the formal definition of the derivative in terms of limits. Using Leibniz notation, the derivative is defined as the limit as delta x tends to 0 of the quotient delta y over delta x, where delta x is a small change in x and delta y is a corresponding small change in y. We also have the variable u somewhere in between, acting like a stepping stone in the composition of functions. And a change in x causes a change in u, denoted by delta u. We can suppose in this sketch that delta u is non-zero, and then insert delta u both in the numerator and denominator of the fraction without affecting the overall value of the expression of which we are taking the limit. But the limit of a product is the product of the limits. So we can rewrite this as a limit as delta x approaches 0 of delta y over delta u multiplied by the limit of delta u over delta x. And we can adjust the way we've written the first limit. Because we expect the delta u to get really, really small as delta x does, that is, delta u goes to 0 as delta x goes to 0. Then recognize the first limit as a definition of dy du, and the second limit as a definition of du dx. This completes the sketch of the proof that dy dx equals dy du times du dx. Here's the statement of the chain rule again with both versions. Let's focus now on the version using the function notation with the dash. The explicit connection is that y is a function u with rule f of u, and u as a function of x with rule g of x. So we're feeding the rule for g into the rule for f, which creates the composite function f circle g, or the composite of f and g. Then f circle g, or the composite of f and g dash x, is the derivative of y with respect to x, not with respect to u, which we had previously just called y dash, also called dy dx in Leibniz notation, which we recognize as dy du times du dx using the earlier version of the chain rule. So we can now write the chain rule as f dash u times g dash x, which is, as we see here, f dash gx times g dash x. Let's practice this version of the chain rule on an example. Let's take these two functions, fx and gx. And we want to find the derivatives of the composite f and g, and then g and f. Of course, we can see the derivative of fx is 3x squared, and the derivative of gx is 2x. So applying the chain rule using function notation, we'll get the composite of f and g, or sorry, the derivative of the composite of f and g is going to be f dash of x squared minus 1 times g dash of x, which is 3 times x squared minus 1 squared times 2x, which becomes 6x times x squared minus 1 all squared. On the other hand, applying the chain rule to these functions but composing in the other order, we have g circle f, or the composite of g and f dash x, equals g dash of f of x times f dash of x, which becomes g dash of x cubed times f dash of x, which is 2x cubed times 3x squared, which simplifies to 6x to the fifth, and this solves the problem. Notice that we didn't need to know the rules for the composite of f and g or the composite of g and f. And we can follow the formula for the chain rule quite mechanically. Of course, we can solve this problem without even using the chain rule. In the case of the composite of f and g, we can calculate the composite and we will get x squared minus 1 all cubed. We can expand that out and then differentiate. And with some algebra, we'll get exactly what we got from the chain rule. And we can do the same for the composite of g and f, and then find the derivative. Now, let us consider some applications of the chain rule in solving some practical problems. I borrowed some content dealing with related rates from some other educators. I think you will find the first one rather hilarious, but illuminating. Then I will conclude with the applications to the Gaussian curve and the ice melting problem.
The chain rule. With a super simple example. Imagine we collected weight and height measurements from 3 people, and then we fit a line to the data. Now, if someone tells us they weigh this much, we can use the green line to predict that they are this tall. Bam! Now imagine we collected height and shoe size measurements, and we fit a line to the data. Now if someone tells us that they are this tall, we can use the orange line to predict that this is their shoe size. Bam! Now, if someone tells us that they weigh this much, then we can predict their height, and we can use the predicted height to predict shoe size. And if we change the value for weight, we see a change in shoe size. Bam! Now let's focus on this green line that represents the relationship between weight and height. We see that for every 1 unit increase in weight, there's a 2-unit increase in height. In other words, the slope of the line is 2 divided by 1, which equals 2. And since the slope is 2, the derivative, the change in height, with respect to a change in weight, is 2. Now, since the slope of the green line is the same as its derivative, 2, the equation for height is height equals the derivative of height with respect to weight times weight, which equals 2 times weight. Note, the equation for height has no intercept because the green line goes through the origin. Now let's focus on the orange line that represents the relationship between height and shoe size. In this case, we see that for every 1 unit increase in height, there is a 1/4 unit increase in shoe size. And I admit that it's hard to see the 1/4 unit increase in shoe size, so just trust me. Anyway, because we go up 1/4 unit for every 1 unit we go over, the slope is 1/4 divided by 1, which equals 1/4. And since the slope is 1/4, the derivative, or the change in shoe size, with respect to a change in height, is 1/4. Now, since the slope of the orange line is the same as its derivative, the equation for shoe size is shoe size equals the derivative of shoe size with respect to height times height, which equals 1/4 times height. And again, because the orange line goes through the origin, the equation for shoe size has no intercept. Now, because weight can predict height and height can predict shoe size, we can plug the equation for height into the equation for shoe size. Now, if we want to determine exactly how shoe size changes with respect to changes in weight, we can take the derivative of shoe size with respect to weight. And the derivative of the equation for shoe size with respect to weight is just the product of the two derivatives. In other words, because height connects weight to shoe size, the derivative of shoe size with respect to weight is the derivative of shoe size with respect to height times the derivative of height with respect to weight. This relationship is the essence of the chain rule. Plugging in numbers gives us 1/2. And that means for every 1 unit increase in weight, beep, boop, beep, there is a 1/2 unit increase in shoe size. Bam! Now let's look at a slightly more complicated example. Imagine we measured how hungry a bunch of people were and how long it had been since they last had a snack. As time since the last snack increases on the x-axis, people got hungrier and hungrier at a faster rate. So we fit an exponential line with intercept 1/2 to the measurements to reflect the increasing rate of hunger. Then we measured how much people craved ice cream and how hungry they were. The hungrier someone was, the more they craved ice cream. But after a certain amount of hunger, the craving did not continue to increase very much. So we fit a square root function to the data to reflect how the increase in craving tapers off. Now, if we want to see how the rate of craving ice cream changes with respect to the time since the last snack, plugging the equation for hunger into the equation for craves ice cream gives us an equation without an obvious derivative. To convince yourself that taking the derivative of this is no fun at all, pause the video and give it a try. However, because hunger links time since last snack to craves ice cream, we can use the chain rule to solve for this derivative. First, the power rule tells us that the derivative of hunger with respect to the time since the last snack is 2 times time. Likewise, the power rule tells us that the derivative of craves ice cream with respect to hunger is 1 divided by 2 times the square root of hunger. So, with these two derivatives, the chain rule tells us that the derivative of craves ice cream with respect to time is the derivative of craves ice cream with respect to hunger times the derivative of hunger with respect to time since last snack. So we plug in the derivatives, bip, boop, bip, and plug in the equation for hunger. and cancel out the 2's, and we get the derivative of Crave's ice cream with respect to time since last snack. This derivative tells us how quickly, or slowly, our craving for ice cream changes with respect to time. Double bam! In this last example, it was obvious that hunger was the link between time since last snack and Crave's ice cream. And we had an equation for hunger in terms of time, and an equation for Crave's ice cream in terms of hunger. However, usually these relationships are not so obvious. Instead of having two separate equations, we usually get the first equation jammed into the second. And when all you have is this, it's not so obvious how the chain rule applies. So we can talk about how to apply the chain rule in this situation. Let us scooch the equation to the left so we have room to work. Now, one thing we can do in this situation is look for things in the equation that can be put in parentheses. For example, the square root symbol can be replaced with parentheses. Now we can say that the stuff inside the parentheses is time squared plus 1/2. And Crave's ice cream can be rewritten as the square root of the stuff inside. Now, the chain rule tells us that the derivative of Crave's ice cream with respect to time is the derivative of Crave's ice cream with respect to the stuff inside times the derivative of the stuff inside with respect to time. The power rule gives us the derivative of Crave's ice cream with respect to the stuff inside, and the power rule gives us the derivative of the stuff inside with respect to time. Now we just plug the derivatives into the chain rule and plug in the equation for the stuff inside, cancel out the 2's, and we get the derivative of Crave's ice cream with respect to the time since last snack. And that's exactly what we got before. Bam!
This is a related rates problem about water being poured in a cone. So let's start by drawing a picture. We have a cone. And our cone, we know some basic information about it. The height of the cone is 8 centimeters. And we know that the radius of the cone is 3 centimeters. And we're interested in how the water that's in it is changing. And in particular, we're interested how fast the water is changing when it is 4 centimeters full. So we have our cone now is at this height of 4 centimeters. Okay, well, for a related rates problem, we are interested in identifying our variables. So let's identify our variables first. When considering the water, there are 3 basic measurements we can consider. We could have our total volume, we have the height of our water, and there's the radius at the top of the cup. So the radius of the water. So let's go identify each of these. We'll color them in red. So my radius is the distance from the center of the cone to the edge of the water. The height is the height of the water from the cup, and the volume is the volume of water that's in a cup. So we have these 3 quantities describing our water, and they are related by geometry with an equation, that the volume of a cone is 1/3 pi r squared h. The second thing we want to consider is what type of information are we given. So as we read the directions, we can see that we're given an information, something's 50 centimeters cubed per second, and as I think about what that might measure, centimeters cubed as a volume per second tells me I have a rate. And so this is a rate of change of volume. Now I'm pouring water in, and so this is a positive rate of change. The rate of change of volume is given by 50 cubic centimeters per second. As we continue to read the problem, we find the information about our cup itself. We've already written that down. And we see how fast is the water rising, and we ask ourselves what kind of question is that. And that represents a measurement of a rate of change of height. And so that's the question that's unknown. So the height rate of change is what is unknown. And finally, we end by saying that the cup is 4 centimeters full, which is information about the height of our cup. So we get that the height of our cup, h, equals 4 centimeters, is some given information. Now the chain rule gives us a relationship between rates of change. It tells us that the rate of change of volume is equal to the derivative of volume with respect to height times the derivative of height with respect to time. And so if I could find the rate of change of volume with respect to height, I would be able to solve this using simply my chain rule. If I look at the formula for volume, though, it actually has two variables, the radius and the height. So my goal is I need to find one equation that relates volume in terms of height. And the way that I do that is I need to think about how the radius and the height are related. This will require finding another equation. The equation is going to be based on similar triangles. If I look at my cone, I have two similar triangles. I have the triangle formed by the entire cup, and I have a triangle formed by the smaller volume of water, which I've labeled below. I have the full cup, which has a radius of 3 and a height of 8, and the volume of water, which has a radius of r and a height of h. I want to emphasize I am not using the number for my height. I use the variable to get my equation. Similar triangles tell us that ratios are equal. So the ratio of height 8 is to 3 is the same as the height of the small triangle, h is to r. And so if I cross multiply, I get 8 radiuses equals 3 times the height. And I want to find a way of getting my volume in terms of just the height, so I'm going to solve for r. My radius is 3/8 of my height. And I'll use that substitution in my volume formula so that I get my volume as 1/3 pi times 3/8 the height, that's the radius, which is squared, times the height. So this gives me my formula for volume in terms of height only. My volume is, what do I get? I get pi times 9, so I get 9 pi h cubed over 3 times 64. I'll just write it as 3 times 64 because I see I'm going to cancel. And so I get 3 pi h cubed over 64. And that's the volume in terms of height. So that I can now use the rate of change formula. The rate of change of volume with respect to time is the rate of change of my formula, 3 pi h cubed, let's do 3 pi over 64, h cubed, And by the chain rule, I get 3 pi over 64 times 3h squared times the derivative of height with respect to time. And now I have it in terms of, I have an equation for my various values. So we can now substitute our values that we know. My rate of change of volume is 50, 3 pi over 64, my times 3, my height is 4, so I get 4 squared, times the rate of change of height, which is the unknown, dh dt. So let's see what simplifies. 4 squared is 16, so that cancels and leaves a 4, and so I get, see, I can divide, and I get the dh dt, oops, change color accidentally, dh dt is 50 times 4 divided by 9 pi. So that's 200 over 9 pi. And that is a rate of change in height, so that is centimeters per second.
G'day guys, we've got a related rates question here today where it's saying that a cube is being increased in size such that the length of each edge is increasing at 0.1 centimeters per second. Find the rate at which the surface area and the volume of the cube is increasing when the side length is 10 centimeters. Now we're going to use related rates for this question, and related rates basically take the chain rule and apply it to working out how two functions relate to each other. So what I mean by this is we've been given the rate at which each edge is increasing. So if we label each edge x, we've been given here dx dt. And that's going to be equal to 0.1. Now, what we've been asked to find is the rate at which the surface area is increasing to start with. So for A, we've been asked to find dSA, or the surface area, dt. Now the way that we use the chain rule to work out what dSA dt is we can say that this is equal to the derivative of surface area with respect to the side length multiplied by the derivative of the side length with respect to time. Now we can see here that if we do take this multiplication of these two derivatives, the dx's will cancel and we'll be able to just have the derivative of surface area with respect to time. So what we've got to do though is we've got to find, make this equation work, we've got to find a function that relates surface area to the side length. Well, that's quite easy. So let's go about doing that first. So we can see that the surface area of this cube here is going to be equal to, there are 6 sides, so 6 times the area of each side is going to be x squared. Okay, well that's not too complicated. So we can differentiate surface area with respect to x. And we can say that that's going to equal 12x. Now we're trying to find the derivative or the rate of change of surface area with respect to time when the side length is 10 centimeters. So we're saying x equals 10. So what we're going to do is we're going to write our function. So this is going to be equal to dSA dx is 12x. multiplied by dx dt, which we're told that the question is 0.1. So what we then do is we input our x value, which we know is 10, and we have 10 times 12 is 120, times 0.1 is just 12 centimeters squared per second. So that's our answer for question 1. Or question A, sorry. Let's go on to question B. I'll change colour. Now, question B is going to be very, very similar to question A, where we are looking for the rate at which the volume is increasing. So we're looking for dV dt. And like we did with surface area, we're going to take the derivative of volume with respect to the side length and then multiply it by the derivative of the side length with respect to time. So to compute this relation, what we're going to do is we're going to have to figure out a volume equation. Now, the volume of a cube or any kind of rectangular prism is length times width times height. So V in terms of x is going to be just equal to x cubed. So dV dx is going to have to be equal to 3x squared. Cool. So what we can do then is we can substitute this into here. We have our dV dx is 3x squared. We know our dx dt is 0.1 from the question. And what we're going to do is to evaluate this dV dt when x is equal to, evaluated when x equals 10, is going to be equal to 3 times 10 squared times 0.1. So 3 times 100 is 300, times 0.1 is 30. Centimeters cubed per second. Cool. So those are our two solutions for part A and part B of this question. Let's just go through how we solved it. So what we had to do is we relate the surface area or the volume in terms of time in terms of two functions. Now, the functions have to be such that the volume or the surface area has to be in terms of a variable that is then, that variable we have in terms of time. So in both of these situations, the dx's will cancel. So once we've computed this, and this can be dx, it can be dt, it can be dm, it can be d anything. But we have to have two relations where we can have the relationship of one thing in terms of another, and then the relationship of the thing that, this original thing, in terms of whatever our objective function we're looking for is. So once we've done that, we then have to just come up with functions for surface area in terms of x and then differentiate them, or volume in terms of x and differentiate them. Once we've done that, we just input all the numbers that were given in the question and go about solving it. Not too complicated. The hardest part, I would say, is just identifying the relationships that we need for this related rates part of the start of the question. So yeah, not too complicated. I hope this video helped. If it did, give it a like, subscribe to my channel, and I'll see you guys again next time.
In this final part of the video, I will demonstrate two contrasting applications of the chain rule. The first application has to do with the behavior of the Gaussian curve y equals e to the minus x squared, which is related to the normal probability distribution used in statistics. The second application tackles the problem of predicting how long it takes for an ice cube to melt away completely. Our first example is the Gaussian curve. which is often described as bell-shaped or in the shape of the bell. Actually, the graph is something called a probability density function for the normal distribution used in statistics. So it's of fundamental importance in applications to science and many other disciplines. The curve is named after Carl Friedrich Gauss, another giant in the development of modern mathematics, who lived and worked from towards the end of the 18th century into the middle of the 19th century. It's a common debating theme: who was a greater mathematician, Euler or Gauss? The description bell-shaped is possibly slightly misleading. There are many curves you could say are in the shape of the bell, but this is the one that most people have in mind when they refer to a bell-shaped curve. I'd like to apply the methods of curve sketching that we have discussed in earlier videos to the function y equals to e to the minus x squared. In the course of doing this, you will see an application of the chain rule. Let's first find the y-intercept, which in this case is 1. There are in fact no x-intercepts, because any power of e, in particular e to the minus x squared for any x, is positive. As to asymptotic behavior, observe that e to the minus x squared, which is the reciprocal of e to the x squared, tends to 0 as x gets arbitrarily large and positive or negative. So the x-axis is a horizontal asymptote. We next look at properties of the derivative. This is where the chain rule comes in handy. Put y equal to e to the u, where u equals minus x squared. So dy du equals to e to the u, and du dx equals to minus 2x. Hence the derivative y dash, which is the same as dy dx in Leibniz notation, becomes dy du times du dx by the chain rule, which now becomes e to the u times minus 2x, which is minus 2x times e to the minus x squared. It's important to know when the derivative is 0. In this case, this only happens when x equals 0. Noting that the factor e to the minus x squared is never 0. We can then build a simple sign diagram by noting that y dash, or the derivative of y, is 0 when x is 0. We have a pattern of plus minus, indicating that the curve is increasing for x less than 0, decreasing for x greater than 0, and achieving a maximum at x equals 0. We can put this together so far by drawing the axes and noting the y-intercept, the asymptotic behavior of the x-axis, both to the far left and far right, and the fact that there is a turning point at the y-intercept when x equals 0. Because the curve is increasing from the left and decreasing to the right, it's natural to fill in the rest of the curve to obtain this bell shape. To create this shape, there appear to be two natural inflections where the curve changes concavity both to the right and to the left. The curve has natural symmetry above the vertical axis because e to the minus x squared doesn't change if you replace x by minus x. Really, it's an instance of an even function. To be sure about the way the curve behaves, and in particular, to find these inflections, we need to find what we refer to as the second derivative. But we presently do not have the tools since we need to know the product rule before we can do this. And we will defer that discussion to a later time when we have covered the product rule. The next example involves some quite intricate mathematics. So you might not be able to follow all the detail at first. I hope you will persevere nevertheless, maybe using the pause and replay buttons on the video from time to time. Because the mathematics describes a very beautiful physical phenomenon with surprising accuracy and involves an elegant and powerful application of the chain rule. In this next example, we've created an ornamental sculpture in the form of a perfect ice cube, which we've suspended from the ceiling in a warm room. 100 liters of water were used to create the original ice cube. We notice after 3 hours that 10 liters of water have accumulated in a tray below the dripping ice cube. Problem is to use maths to estimate the number of hours it takes the ice cube to melt away to nothing. We begin by denoting the side of the cube by x units. What the units turn out to be is really unimportant. It's very important, however, to think of the value of x as a function that changes with time t. The units of time will be hours, since the question actually asks how many hours it takes for the cube to melt away to nothing. You might notice in this example, we are using t as the independent variable and x as the dependent variable. There are two quantities that turn out to be important in the modeling that precedes the analysis. These are the volume of the cube, denoted by v, which is a function of time, and takes the value x cubed for whatever value x happens to be at that particular time. And also the surface area of the cube, denoted by a, which is another function of time and takes the value 6x squared because there are 6 faces to the cube. So we have these 3 quantities associated with the melting ice cube: x, v, and a, all functions of time. In fact, we want to know when the ice cube disappears. So we want the time t at which all of these will be 0. The key physical fact which starts our mathematical modeling is that the rate of melting of the volume of the cube is proportional to the surface area of the cube. This makes good intuitive sense that the surface of the cube is where the cube interfaces directly with warm air in the room. So the more area there is on the surface of the cube, the more associated substance of the cube measured by volume should disintegrate from solid into liquid and drip into the tray below. The rate at which the volume changes with time is the derivative dv dt. And this fact states that dv dt is a constant multiple of the surface area A. Say k times A for some constant k. But A equals 6x squared. So dv dt becomes 6kx squared. We're developing a list of important facts. Note also that dv dx, the derivative of x cubed with respect to x, is 3x squared. We'd like information about the width x of the cube and how it changes with time t. So it's natural to ask what the derivative dx dt might be. The link between this and the other derivative is the chain rule, which in this case says that dv dt equals dv dx times dx dt. But dv dt is 6kx squared and dv dx is 3x squared. So this says that 6kx squared equals 3x squared times dx dt. So dividing through gives dx dt equals 6kx squared divided by 3x squared, which simplifies to 2k. Hence, dx dt is simply 2 times the constant k, which is another constant. If the rate of change of x with respect to time, t, is constant, then the function x must be a linear function of t. The slope 2k, so that x must have the form x equals 2kt plus c for some constant c. This is an important step going backwards from a derivative to a function. It's a fact and a part of a more general theory that we'll explore later on when we come to integration, that if the derivative is constant, then the function that it comes from must also be a linear function. If you think about this geometrically, if the slopes of all the tangent lines of a curve are constant, then the curve must be a straight line. That's what's happening here. Our variables are t and x rather than the usual x and y. This is significant progress to see that v is x cubed and x is 2kt plus c, where k and c are some constants. We haven't yet used the given information that 10 liters of water dripped off the cube in the first 3 hours, which represents 10% of the volume leaving intact, 90% or 9/10 of the original volume. So V of 3 equals 9/10 of V of 0. We can use the fact that V equals to the cube of x to rewrite this as the cube of x evaluated at 3 is 9/10 of the cube of x evaluated at 0. But we know that x evaluated at 0 is just the constant c, and x evaluated at 3 becomes 6k plus c. So we get a nice equation linking the constants k and c. We can rewrite this as 6k plus c cubed equals 0.9 of c cubed. Now solve for c by first taking cube roots to get 6k plus c equals the cube root of 0.9 times c. And some rearrangements gives finally c equals 6k divided by the cube root of 0.1 minus 1. Now we have an elegant relationship between the constant c and k. And we can now find out the time at which the cube disappears by melting away, which is when the width x becomes 0. That is when 2kt plus c equals 0. We can now substitute in the formula for c in terms of k. We therefore want t such that this equation holds. Rearranging the information and noticing that k cancels out, we get that t equals 3 divided by 1 minus the cube root of 0.9, which our calculator tells us is approximately 86.9 to 1 decimal place. Thus, the answer to our original problem is that it takes almost 87 hours for the cube to melt away completely. If you look carefully at the mathematical analysis, you'll see that the final answer depends only on the proportion of the cube that has melted after 3 hours. Clearly, the warmer the temperature, the larger would be this proportion. One could generalize the problem to include this proportion as a variable parameter and deduce a general formula. It's interesting that the model predicts the cube disappears completely. There is a time at which the width and the volume actually become 0. This is in contrast to exponential decay models, with the amount of the given substance tends towards 0. In fact, very rapidly, but never actually reaches 0. In the case of our melting ice cube, the width turns out to be a decreasing linear function of time. We have come to the end of our discussion of the chain rule. And in this final part, we have discussed 2 contrasting examples that relied on the chain rule in order to progress towards a solution. The first looked at the Gaussian bell-shaped curve that is related to the probability distribution used in statistics. And then chain rule helped us in finding the derivative of the associated function. In a future video, I will go further with this example to find and analyze the second derivative. But to achieve this, we'll need the product rule, which will be in the next video. In the second example, we performed a detailed analysis of a melting ice cube. We used the chain rule to connect together different aspects of the problem expressed in terms of derivatives. We obtained a model in which the main measure, the width of the cube, becomes a decreasing linear function so that the cube disappears completely. This is in contrast to exponential decay models, where the value of the function decreases and gets arbitrarily close to 0. but does not actually reach zero. Please read the notes on these two examples and attempt the exercises that are given to you. Thank you very much for watching, and I look forward to seeing you again soon.